Welcome to day 2 of the SLO review. Okay, we're going to cover a couple different topics today that are going to be on your SLO. Remember, you have great advantages and reasons that you want to do good on your SLO, including the fact that it counts as a test grade and it is your final exam if you do well enough. If you don't do well on the SLO, you still get to take another final exam. That's, longer. So y'all don't want to do that. Go ahead and make sure that you do good on this SLO. All right, so the first topic that we're going to talk about is going to be vector components. Then we're going to talk about momentum. And really closely related to the momentum will be the Work-Kinetic energy theorem, followed by circular acceleration. So we've talked about all of this stuff before, but we're just going ahead and reviewing. The first thing that we're going to talk about is vector components. Does anyone remember how to make a vector into its components? Break it up into the X and the Y? Yeah, right? Okay. So the way that we're going to remember this is if I have a vector called A, and I thought I calibrated my board, and apparently I didn't calibrate it well enough. So I'm going to have to recalibrate, possibly. Yeah. It's like all over the place. This is the magic of recording a lesson. Stuff doesn't quite go the way that you always planned for it. And you could start over, but why would you? Okay, if I have a vector called A, and I want to get the components of this vector in the X direction, and I want to get the components in the Y direction, all I have to do for the X is take the magnitude, which is the number that describes vector A, multiplied by sine, for X it's cosine, of the angle that it makes with the positive x-axis. Sorry for those who were watching this later. My microphone battery died, so you might have lost that audio. So AX is the magnitude of vector A times cosine of theta, which is the angle between the x-axis and the vector, the positive x-axis. AY is just going to be A, again the magnitude, the number part of the vector, times the sine of the angle between the positive x-axis and the vector. So I have a couple examples that we're going to run through. And we're going to break these parts into components. So the first example right here, example 1, what we need to do is get the components. We need the AX and the AY. So AX is equal to A, which in this case is what number? 15, times cosine of the angle between the positive x-axis and the vector. So from here to here. So that's 28 degrees. Oops. Degrees, not 280. This is an example. And then we need to figure out what AY is, which is going to be 15, which is what the magnitude of A is, times sine of the angle, which is 28 degrees. So you should be typing this into your calculator now and telling me what we get. So on your calculator, you type 15, you hit the trig button, you go to cosine, and you type 28, and it gives you a number. Anyone have that number for me? 13.24421389929 is what I got on my calculator. How many sig figs do I have? 2. So that means that it needs to round to just 13. For AY, you type 15 into your calculator, you hit the trig button, you hit sine, and then you type 28. And what do you get? You get 7.04207344179. But again, we only have 2 sig figs, so we write 7.0. Now the unit was meters and meters. Pretty simple, but we'll do another one. So this one we're looking for vector D. Vector D is 25 meters, so dx is equal to 25 cosine, and the angle is the angle between the positive x-axis and the vector. So on the figure they gave us 39 degrees, but that's not from the positive x-axis. So what we have to do is go from the positive x-axis. How many degrees are in this first quadrant? 90 degrees. So the real theta that I have is not 39, it's 90 plus 39. Okay? And to do dy, it's just going to be 25 sine of 90 plus 39. Give myself a little bit of room while y'all are typing into your calculator. So on the calculator, very simple again, 25 trig cosine 90 plus 39 inside those parentheses that it made for you. And you get what? Yep, negative 15.73300977762, which means that it would be to 2 sig figs how much? Negative 16. For dy, it's the same thing except you're going to use sine. (19.4286490364), which rounds to 19. Okay, so if I look at this, I have 19. What unit goes on it? Meters. And on the negative 16, I also have meters. What does the negative represent? The direction. Thank you. I'm so glad y'all know that. Makes me happy. All right. And now we're going to talk about vector addition. Okay? So to do vector addition, we break it into components first, add the components, and then after we add the components, we can go back to having a full vector. Now, once we have the components, what we're doing, so we have components of A, and we have components of B. Oops. That's not supposed to be red. So components of A and components of B in the x and y direction. So if I make x and y components, what I form is a right triangle. And once I have a right triangle, y'all can calculate the resultant. So to add vectors, we just break it into the components in the x and y direction. That forms a right triangle. And I'm sure y'all are familiar with the Pythagorean theorem, which is a squared plus b squared equals c squared, or in this case, r squared. So the formula will be a squared plus b squared equals r squared. All right, so we are going to do just one of these examples. If you want to go back and practice, you can do more of the examples with the video. Okay, so vector A is 35 kilometers at 25 degrees north of east. Okay, so 35 kilometers at 25 degrees north of east. If I have this going here, that's saying that vector A is 35 kilometers, and the angle is 25 degrees. Okay? So to get AX, what do I write? (35) Sine or cosine for the x? Cosine of what? 25. To get AY, I do what? 35 sine 25. Type it in the calculator real quick. So 35 trig cosine 25. I get 31.7. Now, this is an intermediate answer, so I'm going to leave it longer, and then I'll round at the end. So this is 31.7. I had 2 sig figs. I'm just leaving 1 extra so I don't have as much rounding error when I get done. And then I'm going to do 35 trig sine 25, and I get 14.8. Okay? Now, to do B, I have 15 kilometers at 10 degrees east of north. So what this is going to look like, I have my whole thing here. This is the north axis. 10 degrees east of north would be all right, my microphone died again. I'm back. Okay, so we have 10 degrees to the north, but realize again that this is not from the positive x-axis. It is a length of 15 kilometers. Okay, so to get the angle, we have to add 10 to the 90 degrees from the first quadrant. So to get bx, it's going to be 15 cosine 90 plus 10. And to get by, it'll be 15 sine 90 plus 10. So what y'all got? Okay, we got negative 2.6 what? All right, negative 2.60. And for the y, we got 14.77, so we'll just do 14.8. Okay, the components of r. So rx is going to be equal to ax plus bx, which is 31.7 minus 2.6. Oh, ry is going to be ay plus by, which is equal to 14.8 plus 14.8. Man, that's crazy. Okay, so 31.7 minus 2.6 should be 29.1. Y'all gonna check me on that? $29.1. 14.8 plus 14.8 should be 29.6. Okay. Now we plug in r squared. The a squared is the rx, so it's going to be 29.1 squared. Plus the b part would be the y part, the ry. It'll be 29.6 squared. And you know we got to take the square root of both sides to get r by itself. So 29.1 squared plus 29.6 squared. And then take the square root. We get 41.5, which rounds to 42 kilometers. To get theta out of it, all we have to do is do tan inverse ry divided by rx, which is 29.6 over 29.1. So you trig tan inverse 29.6 over 29.1. You get 45.4 degrees, which is about 45 degrees. From the positive x-axis, which is east, which this means north of east. All right, so that's how vector addition works. Now we'll get on to the fun stuff. Momentum. Momentum is P equals M times, this is just P equals M times V. So momentum equals mass times velocity. Momentum is equal to mass times velocity. Mass. Okay. So, for this, we're on to our worksheet. So it says, which has more momentum, a 1,000-kilogram car moving at 1 meter per second, or a 70-kilogram person sprinting at 8 meters per second? So this answer is kind of trivial. I'm sure that y'all already know the answer, but we're going to do this problem real quick anyway. So we need to look at the momentum. So our given, we have the mass of the car is 1,000 kilograms. Mass of the person is equal to 70 kilograms. V of the car is equal to 1 meter per second. V of the person is 8 meters per second. The unknown is the momentum. The equation is P equals mv. We go to solve it. We go P is equal to the mass of the car, which is 1,000, times the velocity of the car is 1, gives us 1,000 kilogram meters per second. That's for the car. And then we do P for the person. Is equal to the mass of the person, which is 70, times the velocity of the person, which is 8. 70 times 8 is 560. And that'll be kilogram meters per second. Which one was bigger? The car. The very slow-moving car still has more momentum than the very fast-moving person. Okay? Easy enough. Okay, work-kinetic energy theorem. The work-kinetic energy theorem states that the work is equal to the change in the kinetic energy. So another way of writing it is the force times the distance is equal to 1/2 mv final squared minus v initial squared. So anytime I'm changing velocity, I'm going to be changing how much energy I have. If I have a change in energy, it means I had to have done some work either on the system or the system did work on the surroundings. So that's all that is. It's not too difficult. All you have to do is calculate the change in kinetic energy. And I think one of the problems that I have is going to focus on that. I have to look at it real quick. All right, we're going to look at number 3. Okay, tennis ball may leave a top player's racket with a serve speed of 65 meters per second. So we're looking at a V final after we hit the ball of 65.0 meters per second. If the ball's mass is 0.0600 kilograms, that's the mass, and it is in contact with the racket for 0.03 seconds, what is the average force exerted on the ball? Will this force be enough to lift a person off the ground? So there's a couple different ways you can solve this. We're going to look at it from the momentum energy thing to solve it real quick. Maybe that won't work actually. This will work from impulse momentum. I screwed up. So impulse momentum says F delta T equals the change in momentum, which is M delta V. And then I'm going to see if we can solve the force the other way, and we can't. I screwed up and gave you a bad problem for what I was trying to teach you. But this is also going to work. So, equation, the unknown is force. This is the equation. And we'll go to solve. So force, I don't know. Delta T, I do. It's 0.0300. M, I do know. It's 0.0600. And the delta V is V final minus V initial. So V final is 65. V initial is 0. So 65 minus 0. Y'all can plug it in and solve force that way.
Yes.
So the other thing that we could have calculated afterwards, but we ran out of time due to microphone issues. The rest of the class will probably get this. I'm going to do this and put it up on the video for a first period. Everyone else, y'all will get to continue along. Okay, so. Okay, my microphone is recharged yet again. So hopefully I can get through the rest of this lesson without having to stop again. So what I have here is solving for force. So we just need to divide by what's multiplying by the F, 0.0300. Plug it into our calculator. We get force is equal to 0.0600 times 65 divided by 0.03, and we end up with a force of 130 newtons. Okay. So this is called the impulse momentum theory. That would be that the force times the amount of time that that force is being utilized is equal to the change in momentum, which is the same thing as this M delta V, because momentum is mass times velocity. So the force times the time that that force is acting is equal to the change in the object's momentum. So that's a kind of important one up there. Okay. So we've covered vector components. We covered what momentum is. It's mass times velocity. The work-kinetic energy theorem says that the work that you put into something is equal to its change in kinetic energy. The other thing that we just added, because I forgot to write it down earlier, is the impulse momentum theory, which is that the force times the time is equal to the change change in momentum, which is the mass times the change in velocity. The last one I wanted to cover today was about circular problems, circular acceleration, also known as centripetal acceleration. So, what we use for centripetal acceleration is AC is equal to v squared divided by r. So AC is centripetal acceleration, v is velocity, and r is the radius of the circle that you're turning through. So this could be anything from a car going around a corner or a Ferris wheel that's going around, anything that's circular. Maybe you want to find out what the acceleration is on a CD or DVD or a Blu-ray as it spins inside the drive. All of that can be found using this formula. So let's look at the worksheet that I gave you, and we should have a question on there about this. Let's go number 9. Calculate the centripetal force acting on a 925 kilogram car as it rounds an unbanked curve with a radius of 75 meters at a speed of 22 meters per second. So there is quite a bit of information here, and we're going to end up applying more than just one thing to find our answer. Put it in over here again. Okay. So, like always, we break down things into the given. So we have a 925 kilogram car. Based on kilograms, you should know what this is. What is it? It's mass. Okay? It rounds an unbanked curve with a radius of 75 meters. So the radius is given. It's 75 meters. And it says a speed of 22 meters per second. Now, speed and velocity are very closely related. So usually in our equations, it's a v, not an s or anything like that. So v is 22 meters per second. The unknown that they want us to find is they want the centripetal force. So we want to calculate force. But I didn't give you an equation for centripetal force. I gave you an equation for centripetal acceleration. So what we're going to need to actually find is centripetal acceleration. And then we are going to need to remember that from Newton's second law, that a force is just equal to the mass of the object times the acceleration. So in this case, the centripetal force is the mass times the centripetal acceleration. And we just wrote this on the other page, so AC is equal to v squared over r. Okay, so our problem's all set up now. We have AC equals v, 22 squared, divided by r, which is 75. So go ahead and put that in your calculator real quick. So I have 22 squared divided by 75. And what do we get? It's 6.453333333333, like forever. So since I already have that number in my calculator, I don't need to round it. You know, you don't have to write all the threes on your paper, but keep that in your calculator. We're going to go to the next piece. So Fc, the centripetal force, is equal to the object's mass, which was 925 kilograms, times the acceleration, which was this 6.453 forever, which is inside your calculator already. So on my calculator, I just pressed 925 times, I hit the blue control button that's on the left side, and the negative button which says answer in blue. So 925 times answer gives me FC is equal to 5969.4 Lots and lots of 3s again. Okay, so I go back up to the top. I want to count my sig figs. It's like, how many do I have here? 3. How many do I have here? I have 2. And how many do I have here? I have 2. Lowest number of sig figs is 2, so I round to 2 sig figs. So the 5 is significant. The 9 is my second sig fig. Does the 6 make the 9 round up or stay the same? It rounds up. So that would get me to 6 over here, and then 0, 0, 0. Oh no. I was supposed to have 2 sig figs, but now I only have 1. So how do I fix this? What you should be saying is I need to write this in scientific notation now. So scientific notation, I looked at my decimal is hidden right here right now. I move it 1, 2, 3 spots. And now I can write 6.0 times 10 to the third, because I moved it 3 times. And since this is force, the unit should be newtons. Now force is a vector, so I should have a direction. So the direction of a centripetal force is towards the center of the circle. So center of the circle or center of the curve. All right, so let's recap what we've talked about today. We did components of vectors, we did momentum, the work-kinetic energy theorem, the impulse momentum theory, even though I forgot about it for a second, circular acceleration, and that is all we have. For the rest of the class period, you should go ahead and finish the rest of this worksheet. The worksheet from Monday and Tuesday are both due tomorrow, which is, or from Tuesday and Wednesday are due tomorrow, which is Thursday. I think that's the right day of the week, right? Today is Wednesday? Good. Okay, so everything's due tomorrow. We're going to have one more review session, and we should be taking this SLO on Friday. So study up. Thanks.